Thanks very much. Okay, so just to be sure, I'm Jack and that's Sam, just so everybody's on the same page. And by the way, if I happen to pace off camera, please feel free to yell at me. I have a bad tendency of pacing. So anyway, our presentation will be on causal machine learning and experiments. We're going to divide the presentation into two components. So the first part, we're going to talk about our balanced permutation test paper, which is kind of the first paper we have in this series. So I'll be talking about that, and then Sam is going to give you a sort of broad overview of our plans for projects in this space. The reason why we're doing it this way is because we're very greedy people. We have a book project with Mr. Chris Hare we're working on at the moment, and we sort of really would like as much feedback as we can get on these projects. So that's what we'll be doing. So in terms of questions during the presentation, we're totally happy to be interrupted at any time. So feel free to jump in, and if something's not clear, we'll try and clarify it for you. We're also going to try to leave plenty of space at the end of the presentation for questions. So if you don't feel like being, the economist in the room interrupting the talk, you can just ask at the end. That's fine. Okay. So without further ado, the balanced permutation test, a machine learning replacement for balance tables. This project began with, what we thought was a really simple question, which is, should I put a balance table in my experiment? Should I include a balance table and associated balance tests? If you've never seen a balance table before, which is unlikely, here's just a simple example for a balance table from a simulated 2-arm experiment with 1,000 observations. Here we have 5 pretreatment covariates, female, black, income, Democrat, age, and so on. And you'll see the balance table shows you these sort of descriptive statistics for observations in the treatment and control groups, and then also reports these kind of simple statistical tests, difference in means, across these pretreatment covariates between the treatment and control groups here. If you haven't seen one of these before, this is what we're talking about. And surprisingly, it turns out this is like a highly contested question. If you've never come across this little literature before in political science, there was like a big back and forth roughly in the last, 10 or 12 years or so, where I'm going to, turn it into 2 stylized groups of authors are arguing about whether we should include these tables, and then, what should we do with the information in these tables, if anything at all. Okay, so this is the literature we're trying to enter, and we're going to try and resolve this debate in a way that makes everybody happy. We'll see if that actually works out. Okay, so on the pro-balance table side of things is Gerber et al., 2014. Again, this is kind of a stylized representation. They argue that inference in experiments just depends on successful random assignment. It's pretty straightforward, right? And we know, from reading the published literature that we can have all kinds of randomization failures for weird idiosyncratic reasons. I think the most straightforward way to think about this is, you could have a field experiment. I think field experiments are sort of the biggest issue here, where, maybe you're trying to randomize the treatment out in the field somewhere. You've got lots of people, and things get mixed up, and through some mechanism or other, the intended randomization doesn't work out the way you wanted it to, and you end up with some kind of systematic imbalance that way. Or maybe you run a survey experiment, and you have Lucid or one of these other companies implementing the treatment assignment, so you're sort of giving control over that to some third party, and you're not really sure if it worked until you look after the fact. Another thing that they argue, which is right, is that approximate marginal covariate balance is a testable implication of simple random assignment. By the way, this is only true if you correct for multiple testing. If you don't correct for multiple testing, then as the number of measured covariates goes up, the likelihood you're going to find chance imbalances will go up at the same time. But if you correct for balance, if you correct for multiple testing, that's true. And then last, they say, balance tables can help us catch these assignment or balance issues in practice. Okay. And then there's the sort of anti-balance table point of view. This famous paper, now famous paper by Mutz et al. They come around in 2019. Excuse me. Are we okay? Okay.
That's me.
Sorry. So they come around in 2019, and they say everything that Gerber et al. Say is wrong. Balance tables are not useful for detecting assignment errors in practice, and they list some papers. They say balance tables, probably worse than the first thing, encourage these post hoc regression adjustments and open the door to specification searching. And this procedure that they kind of pejoratively call the balance test and adjust approach, this just isn't a sound estimation procedure at all. We should just have a pre-analysis plan, and we should just, not do these balance tests and tables in the first place. Okay, so this is the literature we're walking into. And just to dunk on the balance tables a little bit, so if we return to our little simple example from the first slide, what if I were to tell you that in the treatment group here, we have no black female observations, literally 0? Okay, so this is another issue with the balance tables. they only check for marginal covariate balance. There's no examination of the joint distributions of the variables. So it could look like you have balance if you just sort of dump your pretreatment covariates into the table, when really you've got some significant problem, okay? So, in this little example, assignment's conditioned by female, black, and income. And if you were to multiple test correct the p-values there, those stars would wash away. So everything would look fine. Okay. So the balance table is not super great. So why don't we just do what Mutz et al. Say and just get rid of them? Okay. So let me give you some intuition for why we're going to argue that you still want to do something here, not a balance table, but something. So if your randomization works and you're interested in estimating the treatment effect of some treatment, what I'm going to call W, on some outcome variable Y, if your randomization is successful, then this third variable Z is sort of, we're worried about some omitted third variable Z. It can't affect W, right? Because the randomization worked. So even if it affects the outcome variable, we don't need to worry about it. It's fine. This is the whole point of running the experiment, right? We could also have imbalance on some irrelevant covariate. So the example I like to use here is like IP address, for instance. So say that you perform an online survey experiment and you use IP address to randomize the groups. And you say odd numbered IP addresses will be in the treatment group and even numbered will be in the control group. Well, congratulations, you have some third variable that is a deterministic predictor of the treatment assignment, but we don't care because it would never affect your outcome variable, right? So, you could have imbalance on covariates that just aren't confounders because they don't affect Y and we wouldn't care. But then we could have imbalance on some true confounder. And this is the thing we're still worried about, okay? So if we have some kind of breakdown in the randomization, it goes awry for whatever reason, and that happens to happen over some confounding variable Z, then all of a sudden we're in this broken space and we could have a confounder again, okay? How likely this could be or not is hard to say, but this is the thing we're going to be worried about, is this sort of last stag on the end here. So we want to be in the universe here where the randomization works and we don't have a problem. We're slightly worried that sometimes we might be in the last stag on the end there. Okay. All right. Just to sort of put this out there such that you don't think that we're crazy people, we just wanted to throw up this quote from Dean Eccles. He had a great blog on Andrew Gelman's website where they were sort of talking through issues related to balance tables, and he had this great quote about how it is true that, like, in theory, if the randomization works and is successful, then we shouldn't need to do any of this stuff. But in practice, right, so he says, we're not infallible, we're going to delegate this decision to somebody else, and then in some circumstances, we're just sort of absorbing information about other people's experiments. So this is a kind of call for epistemic humility, right? Like all sorts of things could go wrong. We agree with this. So we're going to propose a different test, okay? That hopefully I can convince you is a good idea. Okay. So what are we proposing? We're going to argue you can have your cake and eat it too. You can test for balance without inducing these post hoc adjustments after the fact. So to begin with, we think you should take identification seriously, even if you control the assignment mechanism. In causal inference land, right, we're going to spend lots of time identifying assumptions underneath observational designs. We need random assignment to like estimate effects in experiments. We should at least check to make sure things are okay so far as we can. We agree with Mutz. Balance tables are very weak tests of assignment failure. It's like bringing a knife to a gunfight. You don't really know what you're looking for, so we're not going to recommend that. We recommend instead that you load for bear and test for systematic imbalance using machine learning. And I should have mentioned this at the beginning, but the premise underneath this project and much of our other work is, well, we know that machine learning is going to be great for prediction, and we have these great tools now that are very fast and easy to use. So why not use them to test for systematic imbalance in this case? We don't have to use the sort of old balance table idea. And if you happen to find that something goes wrong, there's this new class of estimators. Well, they're not really new, but they're sort of becoming popular. These doubly robust machine learning estimators is what we're going to call them. And if you happen to find imbalance, then you can use one of these estimators to potentially account for selection into the treatment, okay? Depending on how broken the experiment is, it might be too broken to fix, but maybe you could. By the way, maybe you've heard of one of these other names for what we're going to call doubly robust machine learning. These are all sort of flavors of a similar idea, which is we're going to take into account modeling of the treatment propensity, propensity into treatment, and we're also going to model the response surface, and then through a kind of complicated procedure, we're going to estimate effects that way. So there's lots of other names for this. I just wanted to sort of raise that at this point. Okay. What are the benefits of our approach? Well, first of all, we're going to give you a balance table. We're going to give you a balance table replacement that actually could potentially work in practice. It's data-driven. There's no need for post-hoc user specifications. It works with the pre-registration paradigm. You could pre-register everything I'm about to tell you to do. And it's going to work off the shelf with a single line of code. You're happy to, if you want to Google ML balance and then either of our names, you can find the package on GitHub. And you can check it out for yourself. The function is called random check. All you need is a treatment assignment variable and pretreatment covariates. You can just dump it in and it'll do the rest for you. And then there's this kind of fringe benefit. You could also potentially use this to detect experiments that have fabricated or manipulated data. And I'll show you an example of that in the slides as well. That's just kind of a side benefit. Okay, so what are we proposing you do? We propose the balanced permutation test, sort of inspired by Bremen's permutation feature importance idea in the random forest paper. So the first thing you're going to do is build and tune a black box model of treatment assignment using pretreatment covariates. I want to put a big asterisk here. So you don't want to include IP address in here, right, or things like that. You also don't want to put colliders in there. That's a bad idea, right? So we're only interested in moderating or confounding variables. We're not interested in colliders or relevant variables at this point. I'll talk about what the black box model is later, but for now you can just think of it as a machine that you put in an outcome variable and some pretreatment covariates, and it's going to spit out treatment propensities for you. Okay? We'll talk about the implementation a little bit later. The second thing you're going to do is you're going to build a black box model of permuted or simulated treatment assignment. So you're going to take the real treatment assignment vector that you have and just randomly permute it, shake it up, break up any dependencies that there might be between treatment assignment and pretreatment covariates. And we're going to do that with the exact same model and tuning parameters as we did in the first step. This turns out to be kind of important, but maybe we'll talk about that a little bit later. And then all you have to do after that is we're going to compare the two treatment propensity score distributions you get from steps 1 and 2. And we're literally just going to do a kind of ocular test and look at the distributions. And that's sort of all there is. And I'll talk about why there's no test statistic in a minute. But this is sort of how the method culminates. What do you want to look for in this figure? Well, we're looking for differences in the central tendency or variance of the distributions, extreme or deterministic propensity scores that we shouldn't be expecting to see, weird clusters of observations, or like a bimodal distribution, which would be really weird. There was just sort of weird stuff that we're not expecting to see, okay? And that's basically it. I'll talk about the test statistic thing in a second. Okay, so this is what I'm talking about. So here's the result from our method for the simulated example that I showed you at the beginning. On the x-axis, we have the treatment propensity scores ranging from 0 to 1. If you've never seen a treatment propensity score distribution before, so a treatment propensity score of 0, the model is telling us, we're predicting this observation has no chance whatsoever of being in the treatment group. Treatment propensity score of 1 means that we're saying deterministically it will be in the treatment group, okay? And we shouldn't expect to see that in the context of an RCT, right? So in the context of an RCT, the treatment's supposed to be random. Whatever our expectation is where we should expect to see sort of the middle of the distribution, okay? So the orange distribution here is the real distribution of treatment propensity scores, and the blue distribution is the distribution of null treatment propensity scores, okay? So in the null distribution, we know everything's fine. We sort of shook up the y variable here. So we know there's, in this blue distribution, we know that there's no relationship between the outcome and the pretreatment covariates. In the orange distribution, things are not looking good, okay? We have lots of extreme treatment propensities, close to 0 and 1, and it looks kind of like weirdly bimodal. So if you were to see this right away, you would know for some observations, for some reason, something has gone horribly wrong here. And you could just simply look, if you were to just sort the data by treatment propensity and look, you'd see right away, all of these observations that have near 0 treatment propensities are all female and black, okay? So in the package, we have measures of variable importance you could use to simplify this. We have sort of other stuff going on, but simple descriptive statistics, is enough in this case, okay? So nothing too complicated there. You don't need to specify anything, it just sort of pops up for you, okay? All right, so hopefully I'm not losing anybody at this point, but just to be sure that you sort of understand what's going on, let me just show you a version of this figure for an example where everything's fine, okay? So say you run an experiment, there's no contamination of the treatment. We've got our blue and orange distributions, they're almost perfectly overlapping. We have no extreme treatment propensity scores, nothing to worry about, okay? So this is fine. So this is probably what you would expect to see in 95% of cases where the random assignment works and we don't have any weird contamination. Any questions at this point? People okay? All right, keep going. Okay, what if something goes horribly wrong? So you accidentally put your treatment assignment variable as a predictor, so you put the left-hand side variable on the right, or you have some other deterministic predictor. Well, then we have our nice blue null distribution, and then for the real distribution, they're exclusively 0 and 1. Okay, so this would be like something went horrendously wrong. And then here's an example from a real paper. Don't need to talk about the details of the experiment too much. But in this case, this is a recent field experiment that was published in the APSR. They noted a little bit of like weird, unusual imbalance just based on the balance table alone. Our method is able to recover this sort of straightforwardly. You can see the distributions don't really look like the null distribution at all. And for some reason, there's this sort of separation happening in the distributions there. So it works on real data too. And if you were to just, sort of test to make sure that selection into the treatment doesn't affect our treatment effect estimates, we do this in the paper. And it turns out that using the sort of preferred estimator that we like that accounts for treatment propensity, their main effects are totally fine, okay? So in practice, if you had an experiment where something went really wrong and you notice this imbalance, now you have something to do. You can estimate effects that incorporate the propensity score, and hopefully that will, maybe satiate reviewers or editors or so on. Okay. One last thing to talk about. So a side benefit that I kind of mentioned is you can also use this to detect fabricated or manipulated experiments in some circumstances. And the reason why this works is kind of counterintuitive. So for whatever reason, whenever people make up experimental data, it can result in an unusual relationship between treatment assignment and pretreatment covariates. I think part of the reason why this happens is because oftentimes, they're interested in showing a conditional effect over some covariate, so then the fabrication manifests itself in this relationship that shouldn't exist, okay? So it turns out this is frequently the case. We've actually run this on several papers, but I'll just show you one example. So here's an example from Xu et al. 2012. This is a paper that was retracted after the folks at Data Colada did a kind of deep investigation into it. And if you use our BPT test on their data, this was an experiment about honesty, ironically. You can see the null distribution is like centered around 0.5, right? We would expect it to be with just complete randomization. And then the real distribution is like weirdly blocky, which is strange. But then what we're really worried about is this cluster over here, where for some reason, for this cluster of observations, they have near deterministic propensity scores. It would be hard to explain this if the random assignment worked, right? Because we shouldn't be able to recover good models of treatment assignment if the random assignment worked like this. So it won't always catch fabrication, I should say, but it works on all the papers we've tried it on, and maybe there's some sort of selection bias going on there. Maybe there's some more creative fabricators out there who are fabricating their data in a way that's a little bit harder to detect. But at least for the ones that we know about, it works just fine. Okay, so let me talk quickly about why there's no test statistic, and then I'll hand it off to Sam. So we considered a variety of test statistics when we were writing the paper. And the long and the short of it is that none of them work in all instances better than just looking at your data. So we considered location and scale tests, difference in means, difference in variances between the distributions, the Skakoni test. People are probably familiar with the Kolmogorov-Smirnov test. So we considered these. If you were to go back to some of the examples that I showed you, like if you were to just look at the difference in means between these two distributions, the means are almost identical, right? So that doesn't really help. You could have distributions where the variances were exactly the same, but then you have mean shift. So that's not great. So there's really no straightforward answer for a single test statistic to use. You could also consider, just looking at model fit statistics on the null versus the real model.
Jack, could I ask a question?
Sure.
So the KS test is a difference of distributions test, right?
Mm-hmm. Yeah.
So why didn't that work?
Well, so for example, right, like if you were to go back to, so say you have something like, sorry, where's the cluster one? Like with this kind of subtle clustering. I mean, so like in this case, it would probably work. But, say for example, these two distributions look very similar, but then you only had a small cluster of observations, right? It might be the KS test just wouldn't give you the right p-value for that, right? Like you would run it and then you would, like if you don't look at the figure, you wouldn't see this cluster. Because maybe most of the distribution is fine. I don't know if I have an example where most of the distribution is fine. Let's say most of the distribution is fine, you only have a small cluster somewhere else, it's not going to necessarily show you that.
It also gave a bunch of false positives because if you simulate the data, then it's going to be like very precisely around the actual treatment assignment percentage. And so even if there's only like just random, random noise around it, it would give you a false positive and say, oh, these two distributions are different.
Yeah.
So if we go back to your one with clustering, imagine that those outlying ones that were probably fraudulently treated, if those weren't there, then what you're saying, Sam, is that the empirical distribution of treatment propensities tends to be fatter than a large number of observations normally distributed.
That's right.
Like
That's
your
right.
simulation.
Yeah, that's right. That's right. Yep, that's exactly right. Yeah, so anyway, yeah, so we had also considered, you could compare model fit statistics on the null versus real model, so you could compare AUC values or something like that. Again, you'd have to make arbitrary choices about, well, what level of AUC would be enough to conclude that, like, we've improved fitness, right? And you're not going to have any, like, priors about what the model should be, right? Because it should be orthogonal. So, like, there's no real way to think about that. And then last, you could do something like what they do in this Gagnon and Bartesh paper is you could do this many, many, many times over, and then you could compare, say, the model fit statistic for a single, the single run that you happen to have versus permuted versions. Again, when I tested this out, it didn't work for the clustering thing. So maybe that would work for some of the other examples, but at least for clustering, this wouldn't work either. So anyway, we came to the conclusion that we couldn't find a single test statistic that works, and also we were worried if we proposed one, then people wouldn't look at the figure, which seems like a bad idea to us. So ultimately, we come to this kind of simple, simplistic conclusion of just sort of looking at the distributions, and that seems to work generally. Some technical details, I don't want to go too far over time here, but I'll just briefly mention, so the black box that we're using in the paper, these are honest n-step boosted random forest models. It's totally fine to not be familiar with this. It's basically a sort of fancy version of random forest that employs sort of built-in subsample splitting. This is going to make it easier for folks to use this without needing to do custom model tuning. Random forest is a good idea in this case also because unlike some other algorithms you could consider, right, the number of tuning parameters is relatively small. Out of the box, you're likely to get pretty decent fit. So for this application, we think this is good. Also, we're building on this GRF architecture, which is fast and multi-threaded, and you don't need a GPU or anything to run it. So, okay. In the real world, if you wanted to use something else, it could be fun. Okay, I'm gonna breeze past this and pass it off to Sam. So, just to wrap up, so the balanced permutation test is implemented in our R package I mentioned, so you can try it out yourself. Just Google the package name. Yeah, I think that's it. So I'll pass it on to Sam. Here you go.
Thanks. Okay, I'm guessing everybody can hear me. Yeah. Cool. So this section of the talk is just going to be talking about other projects sort of in this causal ML space that Jack and I are interested in working on right now. So let's just talk a little bit about motivation, right? So there's a rapid expansion of the literature in this space. And this is like constantly evolving. So honestly, some of the stuff we'll be talking about here, like specific algorithms, will surely change in the next year. But there's really a lot of promising areas for how machine learning can be adapted and be used in the context of experiments. And probably one of the biggest ones is specifically for subgroup analysis or the calculation of conditional average treatment effects, right? And so let's talk about a few of the methods that we already mentioned. So like causal forests, we have Bayesian additive regression trees. If you want a Bayesian flavor of this stuff, we don't touch it, but feel free to if you want. And then there's also even stuff very fancily named split-weighted conformal quantile regression. So there's a bunch of different kinds. This is literally just 3 out of probably dozens and dozens. But generally speaking, right, so these offer powerful approaches for investigating heterogeneity in treatment effects across subgroups. So it's very useful in the context of experiments. And so here's just kind of a motivating example. So Jack and I have a paper with another co-author, Nico de la Cerda, where we're interested in basically predicting people's responses to partisan endorsements of policies. We were really interested, okay, is it affect or ideology? Is it people's feelings towards parties, or is it their ideological preferences that really fuel this? And so using these methods, we're able to recover these very precise estimates. We're able to explore conditionality. And what we find is that affect is the main driver here. But this is just a little bit of a motivation. And one really cool thing you can do too here is you can look at multi-dimensional conditional average treatment effects. So here we have a partial dependence plot. On both axes, we have different measures of affect. And what we find is that when individuals are affectively polarized on both dimensions, they have much more negative responses to out-party endorsements of policies. And when they're low on both or one, then they have less, right? So kind of an interesting multi-dimensionality here. And great. These methods are amazing. They're really, really cool. Jack and I are big proponents of it, obviously, but there's a lot of potential for misuse. If people are not familiar with machine learning methods in the first place, there's just a lot of mistakes that can happen going through this process of analysis. And Rakovic points this out well in 2021. So let's go over an overview. So our goal here is to provide a clear framework for researchers to apply machine learning tools for their own experimental analyses, right? And so our approach is kind of three-pronged. So the first is let's create the guidelines specifically for how people should use these for subgroup analyses, detecting heterogeneity in their treatment effects in the first place, and then calculating conditional average treatment effects. We also want to outline other useful applications, as we did in the first chunk of this paper or this presentation, right? So machine learning for determining balance or systematic attrition, also using it for measurement, AT estimation, et cetera, et cetera. And our other goal too, to kind of decrease the barriers to entry for actual end users, is to develop a package family called MLC, Machine Learning for Causal Inference, that implements these approaches in a very easy to use but robust way. The goal is that it just works off the shelf, easy to use, similar to the declare design framework, if you've heard about that. And one component is already complete, as we kind of pointed to, which is the ML balance component. So again, we have another simple question, as we did in the first chunk. How should we calculate conditional average treatment effects? I'm sure if you ask any given experimentalist, they're going to have a different answer. So the first one is, okay, well, how about we just interact all of our covariates that we're interested in with our treatment assignment, right? And just see what pops up, see what's statistically significant, see what the coefficient sizes are, right? Well, that's a bad idea. Could very easily overfit to your data. It's most likely misspecified because we don't actually know the true data generating process under here. And it's important to remember, we get really nice causal inference guarantees for our ATEs in a randomized control experiment. But the moment that we're looking at subgroup analyses or conditional effects, we no longer have those causal inference guarantees. We're in observational data analysis land now. Number two, you can also separate into single interaction regression models. So you're interested in the conditional effect of ideology, you're interested in the conditional effect of affect, you estimate different models, right? And you interact those with your treatment assignment, see what pops up, et cetera. Well, omitted interaction bias, as pointed out by Blackwell and Olson in 2022, is a massive issue here. So this is also a very bad idea. And number three is, well, you can use off-the-shelf machine learning methods if you really wanted to, so like a random forest or boosting machines, but they're not designed for causal inference, and you don't get a lot of the nice guarantees that a lot of the methods that I mentioned earlier, like causal forest or BART, actually give you. And the last question is like, do we even have heterogeneity in our treatment, right? So that's a really big question that I think people don't really engage with as it stands. And so this kind of led our journey down the rabbit hole of exploring all of these methods and how they should be used. So two works in political science previously have covered this. So we have Green and White that kind of just introduces the methods to political science as a book chapter and just talks about it briefly, doesn't go into much detail. And then Rakovic does offer a pretty nice detailed general checklist about conducting specifically subgroup analysis with ML. Recommends some nice things that I won't get into. But really, broadly speaking, there are no guidelines from the start of the process, so basically the design of the experiment, the registration of the experiment, all the way to analysis and interpretation. Those just don't exist. It's sort of piecemeal, and we do actually disagree with Green and White and Rakovic a little bit on some of their recommendations. So here's our checklist. This is a very broad overview, and the basic idea is transparency over simplicity. So first, we want to design a clear experiment and check expectations. Machine learning is not a panacea. If you design a garbage experiment, it will give you garbage results. So it is very important to make sure that you have clear expectations, clear hypotheses. You can use the declare design framework to simulate data and check these hypotheses. Highly recommended. Number two is important that these machine learning algorithms change kind of the calculus when you're designing this part of your experiment. You should liberally and accurately measure all the relevant covariate space. By accurately, I mean you should really leverage unsupervised machine learning, or what's also called measurement or scaling. That's really important. If you have a bunch of multicollinearity, these methods can't handle that either. But you should also measure a lot of variables, maybe some that you have a hunch about but aren't well established in the literature, because it's able to deal with what's called the cursive dimensionality much more easily. You don't have the same issues as you do with parametric model. So you should also, as we mentioned in the first half of this presentation, test for assignment failures and or systematic attrition using machine learning, depending on the context of your experiment. You should create and tune an accurate model, which we'll talk about a little bit more later. But basically, like, you want a model that actually has really good predictive capacity. We're working in machine learning land here, so we want to make sure that we get good predictions from our model. Otherwise, we can't really trust what it says afterwards. And then we want to test for and identify treatment effect heterogeneity using that entire covariate space that I talked about. So one of the nice things is you just dump in your pretreatment covariate matrix. You don't specify the modeling like you do in like OLS, for example. For each treatment with identified heterogeneity, and I'll talk about the tests for these, you should report variable importance, and you should explore what variables are actually fueling this heterogeneity. And then you should only present conditional average treatment effects if that variable is identified as important, which I could talk about more later too. And then finally, you want to present your results from doubly robust machine learning estimation, both your ATEs and CATEs. What we found in a lot of simulations is DRML is just straight up better than difference in means estimators. And you should also, though, just as a sanity check to make sure you didn't screw anything up, also report your standard ATE estimates somewhere in your paper. So these are the ones that I'm going to go into detail for the rest of the presentation. So first, let's talk about measuring covariates. So given the ability of these algorithms to handle, as I noted, these large covariate spaces, researchers should consider alternative explanations. You are basically able to explore many more possibilities, many more combinations potentially. So you don't really have to worry about this specification issue where you have to, either you have misspecification of your model because you saturate the regression with all your variables, or you do those like separate single interaction variable models. However, I will note measurement is still incredibly important. If you have bad measures of some underlying concept, again, supervised machine learning is not going to help you out of that. So it's really important to leverage unsupervised machine learning or measurement and scaling to not get the garbage in, garbage out situation. That's basically what I was saying. And then, so the final section of this presentation shows the benefits of accurate and broad measurement in a real experiment. So actually, we're not doing that little part, but so ignore that. But anyway, we'll talk about creating and tuning an accurate model. So really, we want to make sure that a model provides relatively accurate predictions, right? And broadly speaking, this is underappreciated in a lot of contexts. I think this should be more of a consideration even in parametric estimation of models, whether it's OLS or MLE, et cetera, et cetera. But in this context, we certainly want to make sure. And the reason why is that this is related to quality inference, right? So if we have a model and it barely can predict our outcome, let's say it's a 0-1, right? And it's just getting misclassification, it's worse than just guessing, right? Then really, can we say that there's an underlying relationship, or can we be really confident that there's an underlying relationship between our independent variables and our dependent variable? That's something to think about. And published work using causal forests has already made the mistake of not tuning methods well. Not to throw these people under the bus, but if you look into their code, you look into their analysis, they did not do a great job using this causal forest method. So this is already an issue, right, of people not knowing exactly how to build these models. And there's numerous tests for ensuring model accuracy, depending on what your outcome is, what you're interested in. And generally speaking, multiple should be reported, or the ones that sort of fit your research question at hand. Let's move on to testing for heterogeneity. So researchers should always test for treatment effect heterogeneity if they have some set of pretreatment covariates. And it should be used using all of the covariates that are related. Again, like as Jack pointed out, you shouldn't be including variables that probably have nothing to do with the outcome or could be even related in more negative ways to treatment assignment. And there's a bunch of tests. I'm not going to go through these, but these are just 3 offhands that are really easy to implement and we're interested in implementing in our package. And generally speaking, conditional average treatment effects should only be investigated if there's evidence of heterogeneity in the first place. So if these tests say, yes, there's heterogeneity in your data using all of the covariates, and then exploring using variable importance to see which variables are leading to that heterogeneity, only then should you actually be exploring these conditional average treatment effects. And let's just talk really quick about doubly robust machine learning.
If you want to leave 15 minutes, you got about 2.
Okay, cool. So broadly speaking here, we have 2 models. One is we're estimating an outcome, Y, right? Then the other is treatment assignment, which is D. So Y is our outcome variable, D is binary. Technically, this can handle continuous, but let's just work with this. Then you have a vector X, which has all of our pretreatment covariates in it. And then zeta and V are just random errors. You could ignore those, not a big issue. And so the real big thing that we're doing here is we want to model G naught X and M naught X. So G naught X is the relationship of all of our pretreatment covariates with our outcome of interest, right? And then M naught X is our relationship of all of our pretreatment covariates with treatment assignment. So if there's any imbalance or any systematic assignment, right, that will pick it up. And broadly speaking, in this setup, G naught X and M naught X are what we would call nuisance parameters. We don't really care about them. We just know that they bias our estimates if we're not able to predict them well and basically drop them from our models. So the goal here is we only need really good predictions. And that's when we leverage machine learning, much better at prediction than parametric options. And so in the experimental context, if you have good randomization and there's not any significant issues, this just turns into a fancy regression adjustment. But importantly, we are not specifying how to adjust this regression, right? There's no specification from the individual user because we're including all of the covariates. Depending on the implementation, DRML employs crossfitting or other forms of sample splitting, and this just makes sure you don't overfit to the data that you're training your model on, that it's generalizable. And specifically, we employ a variant of DRML where the plugins are honest random forests. You can get gains from other modeling strategies, but again, this is, it's a fast-moving field. It's going to change. But right now, it's very fast and it leads to a lot of high-performance results. I've already kind of talked through these, so we'll just run through this quickly so we can get done. But I will stress this last part. So there's a lot of literature that says that doing this is great and that it has a lot of benefits, even proven in like asymptotia with causal forest. There's a lot of guarantees. And we did this really large set of simulations as well. Let's cover here. So we had 480 permutations of different data generating options. We ran this across 2,000 different seeds to get 960,000 simulations. Here, what you're seeing is the darker the purple color, the more average reduction in absolute error you see for causal forest estimate, the doubly robust machine learning estimate, compared to these more standard approaches. So difference in means, regression adjusted, and Lin adjusted effects. And as you can see, there are some massive performance gains here, and they're massive or they're significant across all of these different options: number of covariates, the sample size, low, medium, high error variance. And so what we found, and again, we used untuned models here. So we didn't even tune the model very well, which means like we didn't get it to fit super well to every single one of these DGPs since there was 960,000. It wins in 99% of the cases. Only 19 out of 1,400 comparisons does it actually fail, that it's marginally worse than these other options. So a lot of evidence suggesting you should just be using doubly robust machine learning for your ATE estimation. So here's just a quick summary of future work that we're interested in. We want to apply this to systematic attrition detection. We want to basically show, similar to these results right here, that it's really good for just basic treatment effect estimation, right? We also really care about, as you might have noticed, this idea of measurement. I started my graduate student career kind of focused more on measurement than supervised machine learning, and I think that's really important. We're also interested in like, well, okay, well, what are the implications of using these models for like pre-registration, experimental design, et cetera? And then we're also really interested in doing this, and we've already started with one paper of a meta-reanalysis of conditional average treatment effects across experimental political science. And so we have a few questions for you. So If you have any ideas on other prediction tasks, like in the context of experiments where it would be useful, we pointed out like imbalance and systematic attrition. What are you skeptical of? So like, what do we need to do to kind of convince you of these benefits, right? So this is a new kind of paradigm shift. And what's confusing? So, Jack and I have been working in this space a lot for the past like 2.5 years. And so we know these methods can be really confusing and it can be kind of esoteric. So pointing any of that out is helpful. And that's it. Yeah, thank you.